Okay, as always, can I just get, a little bit of a response from the audience that you guys can see me, hear me, see the desktop, that kind of stuff? Anything in the Zoom chat, or just say hello. It's good to see you all on this. Okay, we got a thumbs up from Nathaniel. Thank you, Nathaniel. Got a hi, good morning, hello. Thank you, everybody. Good morning to you. Looks like it's struggling to become a nice day out. I hope it makes it that way. It started snowing this morning, which is a bit weird, but oh well, it looks pretty out. So let's continue where we were before. We were talking about capacitors, and what we've seen so far is we have a capacitor. If we hook it up to a battery, we're going to cause charge to flow, and there'll be a positive buildup on this side, a negative buildup on this side, until that potential difference across the battery is the same across the capacitor. When this happens, this equation here, which I introduced last time, was Q equals C delta V. So C is a characteristic of the particular capacitor. It could change depending on the geometry or the dielectric that's used in the capacitor. But the equation is general in the sense that the amount of charge that's going to build up on this plate is going to be proportional to the amount of voltage, the potential difference. And this governing equation, this equation here is kind of the best analogy that I could give to it. Is that it's sort of like Ohm's law. It's, we have the thing that's causing things to happen, which is the change in potential. The reaction is the charge build up on this parallel plate, and the factor of proportionality is the capacitance. And that's not so different from Ohm's law in the form I equals delta V over R, where the current is the response, the potential difference is the cause, and the factor of proportionality is the resistance. So, that's how I look at this equation. I don't know that it has a name. It's not named after somebody, but we could call it, Mr. Ohm's cousin's law, Q equals C delta V. I don't know. So let's move on. That's where we were at last time. There's two things that I want to introduce today, two straightforward concepts. One is the idea of equivalent capacitors, and the second is RC circuits. Equivalent capacitors, what we're going to find here is that this is very similar to equivalent circuits with resistors. Even down to the equations are kind of similar, spookily similar. So I hope that we can get through both of these topics. The first one will be on the exam. The second one is going to be on the group work, but is not on the exam. I'll tell you when we hit that demarcation. So the idea here is capacitors. I have a battery. I have three capacitors, C1, C2, C3. These are measured in farads, some weird SI unit. And if I want to find the equivalent capacitance instead of these three capacitors, in the same way that I was trying to find equivalent capacitors, equivalent circuit with a bunch of resistors, well, in this case here, these guys are, these guys are, these guys are in parallel. How do I know they're in parallel? Because the potential difference across each of these capacitors is the same, right? They're all wired along this wire here. They have the same high potential. They're all wired along here. They have the same low potential, the low side of the battery. And remember, in these diagrams, we're supposed to imagine that these are perfect wires. There's no resistance. There's no ohmic voltage drop at any point along here. It's all the same voltage. So this guy has the same voltage as this guy, and it's all provided by this battery. They are in parallel, right? The same delta V across all. When I have that situation, I can just take the algebraic sum of the individual capacitances. So if this was 1 microfarad, this was 2 microfarad, and this was 1 microfarad, I would get 4 microfarad. They just add up algebraically. Nothing special about 3. I just, it's easy for me to draw 3. This you can continue off to 10 or 20 or 37 or just 2. That's what this ... here signifies, is that, it could indicate any number of these capacitors. As long as they're in parallel, this is your way of creating that equivalent capacitor. The other option that we have is when the capacitors are in series. And series here means the same thing as when we were talking about resistors. Head to tail, head to tail, head to tail, all in a line like this. So the potential difference across each of the individual capacitors, we have this potential provided here, but instead of what we had in the previous situation, we have head to tail, head to tail, head to tail, and these three capacitors signified by C1, C2, C3. If I want to find the equivalent capacitance, in both of these situations, I'm skipping, 3, 4, 5 minutes of derivation to get you these equations, because you guys don't really enjoy that. At least when I remembered in the lecture hall, that was when people got kind of unhappy faces. And it just doesn't really help that much to understand what's going on. But if you like the derivations, and I know there's a subset of people who do, it's pretty straightforward, and it's right in the book. It just takes 2 or 3 lines. You can get these equations very, very simply from first principles. I don't need you to do that, though. So here's what you get for the equivalent capacitance in this particular case. When they're in series, we have this reciprocal addition, that the equivalent capacitance that we could replace these 3 capacitors with would be 1 over C1 plus 1 over C2 plus 1 over C3. Okay, this should look kind of familiar to you, spookily familiar to you from when we were doing resistances. The last thing I want to mention here is there's nothing special about 3. I could do this with 2 capacitors. I could do this with 27 capacitors. That's what the ... signifies. Now, our 2 formulas, see, this algebraic sum and the reciprocal sum. The algebraic sum is for parallel. The reciprocal sum is for series. This looks exactly like the equations for resistors, except that the series and the parallel are switched. So in the case of series resistors, remember that was the algebraic sum, and here we have the reciprocal sum. In the case of parallel resistors, that used to be the reciprocal sum, and now we have the algebraic sum. So it's, there's one nice part about it is you kind of only have to memorize this once and then flip the switch in your head when you're talking about resistors or capacitors. Or you could look at this as a danger point where, hey, these equations are kind of similar, and if I'm not careful, I'm going to use the wrong one. So what I recommend is that you circle back to the definition of parallel and make sure that you understand what it means for either a bunch of resistors or a bunch of capacitors to be in parallel. And it's all about whether the voltage across them is the same or whether it is not. Okay, so that's my my 2-minute heads up that hopefully can help you as you're working with that. My computer is amazingly slow today, so I did not want to kill that. That was a bad idea. Okay, so let's push forward. Now, this equivalent capacitance, so this is the first time that this has happened, that my computer is so bloody slow that I can't even do anything. Let me kill some things. Apologies out there. This is not fun for you to watch. Not sure quite what is doing that. Okay, I guess I've been lucky so far that up until now the technical problems haven't been so bad. But here we go, some technical problems. So let's do some examples. We have 2 capacitors in series, and the capacitors, so the capacitors are in series. The answer is A, they are in series. I've got them hooked up to a battery. And how am I going to find the equivalent capacitor? Well, if I've identified that they are in series, then I go back to my formula here, and it's going to be this reciprocal formula. So I have 3 microfarads, 6 microfarads. I go 1 over 1 over 3 plus 1 over 6. 1 over 3 plus 1 over 6 is 0.5. I'm stuck with this kind of weird units for a moment, which is inverse microfarads. And the 0.5 comes along just from the numerical part of it. in order to get that equivalent capacitance, I have to take one more inversion. And 1 over 0.5 gives me 2. And the inverse of inverse microfarads gives me a microfarad. So long story short, I have this 3 and this 6 microfarads in series. I get a 2 microfarad equivalent capacitor could replace and behave exactly the same as these 2 capacitors. So there's 2 ways of looking at this. One is, hey, I have a complicated circuit. I want to make a more simpler circuit so that I can save components, or I can make it smaller or something like that. Well, I could replace these 2 with that equivalent capacitor. Or I just want to simplify the circuit so that I can analyze it more easily. And in that case, I just kind of mentally replace that 6 and 3 with a 2, and now I know how that jumble of capacitors acts. You could imagine that, you know, if you have 10, 20, 30 capacitors, this can be a very powerful technique to make your life a lot easier, and that's why people do it. Okay, so that's our first numerical example. Let's take a look at our second example here. So this guy, we have a 5 microfarad and a 1 microfarad capacitor. What I'm going to ask you is, I'm going to launch a poll here and see what you say. Hopefully you can see this poll, and this is kind of just making sure that I'm not talking to myself. I have a poll up here. Is this 2 capacitors in series, or are they in parallel? And fairly straightforward, no calculation here, just to see, you know, see how people are doing. You should see either an A or, you know, A, B, C, D, E. Really, your choices here are between A and B. Okay. Okay, I think most of you have finished here, so let's end the poll, see what we got. I can share the results with you. These are in parallel. And how do I know that? Because the potential difference is provided by this battery here. It's provided along this kind of perfect wire. There's no voltage drop along that wire. You're not supposed to think that there's any resistance in it. It's an idealization. I agree. It's not exactly perfect, but it's pretty good approximation. So in this, we have the same voltage across this guy and this guy, and that's basically the definition of being in parallel. Okay, so that's for the 17% of you that didn't get that. That's really kind of something that you want to think about, ask me questions about, or try to review that. You know, how to tell when your resistors or capacitors are in series or parallel. Because if you don't do that, you're not going to be able to figure out which equation to use, and you'll just get the wrong answer. Okay, so in this case, we have that they are in parallel. Parallel for capacitors are my simple situation. The series is the complicated one. My simple situation is the algebraic sum here. So if I look at the algebraic sum, it's nice, it's simple, it's just 5 plus 1 gives me 6 microfarad. And in the end, the equivalent circuit of these 2 capacitors is this single 6 microfarad capacitor. But you have to be careful. There's that subtlety there that you have to figure out whether they're in series or parallel in order to be able to do this. Okay, so that's the first part of this lecture. That's the demarcation for stuff that's on the exam. The next one is actually, I think, a little bit more interesting and a little bit more fun, but this is where the material for the exam ends, is these equivalent capacitors. Because I think I put some of these equivalent capacitors on the homeworks, and there was no RC circuits on the exam. So I'll pause here for a moment. Again, please feel free to use that go slower button on your participants window, or ask questions in the chat. I'm happy to do it. I'm going to just pause here for a moment and and give you guys a second to digest. Is this week's group work for Friday the material that will be on Monday's exam? Yes, Catherine, I think that's the plan. I think Dawn is going to do, as we have for every exam so far, that the last group work right before the exam is practice work for the exam. Okay, so yes, I believe that's true. So tune in on Friday and see the group work. And Troy says, "Thank you for doing that. You're welcome." It's, you know, that's Dawn that puts that extra effort in there. Although I do help her a little bit. Okay, so let's move forward. Thanks for the feedback. I appreciate that. Okay, so RC circuits. We so far have dealt with capacitors and resistors by themselves. You would not, in reality, very often have a simple circuit with just one of these. I guess the one example that makes sense would be something like a light bulb and a battery, and that's about the most useful thing that you can do. What becomes more powerful is when you start combining these, and the simplest combination is we can have one resistor and one capacitor. We call this an RC circuit, right? So an RC circuit is just like you said. We have an R, we have a C. I'm adding one new component in this circuit, which is a switch, and the switch allows me to interrupt the current, or the ability for the charges to flow from this point to that point. So I start my situation in this RC circuit with my capacitor plate charged, right? I've come along with two wires, and I've applied a potential difference across this, created a charge separation. So I have positive on that plate and negative on that plate. And nothing's going to happen to the resistor because I've interrupted the circuit. It does not matter that you have this connection here. Remember, the charges can only flow through a completed circuit. It can't do anything here. It just kind of, there's nowhere for it to go. So it has to have this complete circuit to flow all the way around. But my switch allows me to do that. So I'm going to close that switch. And what's going to happen, these positive charges, we're going to think that they flow from high potential to low potential. So they're going to rush around this circuit. But there's only a certain amount of charges that I put on this capacitor in the first place. There's a finite number of charges. And once I close that switch, they're going to flow off, and everything is going to flow until we've reached equilibrium. Remember, that's our guiding principle when we're dealing with these circuits, when we're dealing with electrostatics in general, is that nature doesn't like it when positive and negative are far apart. It wants them to get close together, and by any means necessary, if it's possible, it will balance those charges. So what's going to happen is we'll have an initial large flow of current as those charges rush around to meet their negative counterparts. But after a while, there'll be a balance between plus and minus, and that current will stop, right? So it starts at some maximum value, that initial gush of electric current as the charges flow around the circuit through the resistor and land at the low potential over here. That will decrease to zero over time. This is what that behavior will look like. If you actually put a ammeter or a current meter into the circuit and measure the current as a function of time, what's going to happen? It'll start with this initial rush of current, and then as the current that you started with, or as the charge that you started with moves around that, there's nothing replenishing it. This is not a battery. That charge gets depleted, and the current as a function of time will decay. This is if you actually measure this empirically, what you'll find is that this is exponential decay. Exponential behavior is something that pops up again and again and again and again in nature and in physics and in biology and in chemistry. It just is something that over and over again governs physical behaviors. And for example, exponential growth of viruses in unwilling populations, exponential growth of populations of animals in nature, exponential decay of nuclear radioactive materials. over time. These are all governed by the same kind of simple equations. I have a question here from the audience. What exactly is a capacitor and what is its function? Francis, a capacitor is two parallel plates that are basically used for storing charge. We've been talking about them. I, I hate to be snarky, but I've been talking about capacitors for the last 3-4 lectures. So a capacitor is something that is used to hold charge. The one plate has a positive charge on it, one plate has a negative charge on it. The governing equation for it is that the charge is proportional to the potential difference across it, okay? So I hope, you know, what is its function? That's a bit more of a subtle question. It's a device for storing charge, and if you think about the separation of charge as being, you know, causing a potential difference, it's a way of storing potential energy in a circuit, and that can be extremely useful if you temporarily want to store energy for a moment, or if you want to be able to generate a large flux of current very quickly. For example, you could short off the plates of a parallel plate capacitor and create a very instantaneous large jolt of electricity that you might not otherwise be able to create in your circuit. Okay, we have another question. Okay, so Francis laughs and says, yeah, I know, but I lost track of what it actually does. Thanks, though. I hope that explains. It's okay, Francis. We get deep in the weeds here and we kind of forget the big picture. So I hope that helps explain. Haley M asks, do all circuits go from max value to 0 or only RC circuits? This is going to be a behavior of RC circuits, Haley, but we're going to see that RC circuits can mean a couple different things. So if you're patient with me, I'll step our way through a couple RC circuits here in the next couple of minutes. But this time constant thing, this time constant behavior is the kind of the signature behavior of RC circuits. So I have this current, this exponential decay. The equation I didn't get to yet was that the current as a function of time has this exponential behavior. This is the number E, it's a special number in nature. It pops up again and again and again. We raise it to the exponent negative time over something called the time constant, right? This is a constant, and it's going to be specific to each circuit that we look at. This is the time, this is the, how many seconds from when we've closed that switch and created that current flowing. So we also will find the same behavior for the voltage. The voltage starts at some large maximum value and then decays over time with almost the exact same equation, e to the negative t over tau, where this initial, first large amount of voltage decays over time. Why is this happening? Let's go back to our circuit. And what happens is in the first instant when I close this switch, the potential difference across this resistor is whatever the potential difference was across that capacitor. But the current is depleting the charge on the capacitor, discharging that capacitor through the resistor until we have a balance. So that large initial potential difference that is existing across this resistor then decays with time also, okay? So these time-dependent circuits, this is the first kind of interesting behavior we've seen in these circuits that has a time dependence, is going to be governed by this time constant. And I'm gonna just introduce the time constant, and then I have to start up a little lab here to show a demo. The time constant without derivation is given by the resistance of the resistor in your series and the capacitance of the capacitor in your series. So this guy is given in ohms, this guy is given in farads. An ohm times a farad turns out to be a second, okay? So the units are ohms, farads, seconds. And all I need to know about the time constant of this is I have to know the resistance, I have to know the capacitance. Let me try to build you a circuit here. My computer was going nuts there for a second, so I had a beautiful circuit build up. Let's build it up from scratch again. So I have a battery. I think I want it this way, I'm not sure. I want it this way. I want a capacitor. Hopefully you guys have played with these kind of circuits in your labs. If not, it's PHET. I'll put a link to this in the on Canvas. We have a nice little light bulb here, and what I want to do is throw in some switches, and then build this all up. So okay, this is oddly satisfying to build these, so I do encourage you to, you know, play around with these sometime if you like. Although sometimes it's very frustrating that it wants to make connections that you don't want to make. So let's build that there. Throw some more wires on here. Come over here. Okay. There we go. So my first circuit is just a battery that I'm going to use to charge this capacitor. Bam, right? I don't know why I caught on fire there, but I caught on fire. And then let's make this, let's give this some healthy, more volts. I want more volts than just a measly 100 volts. Let's do about, well, I don't want that many volts. I don't want to blow up. There we go. Let's do like 1,000 volts. Let me close that again, gets a large amount of charge on those capacitor plates. Then my light bulb is going to be my resistor. And okay, here we go. Almost done. Thanks for your patience on this. I had a beautiful version of this built right before lecture, and then my computer was going crazy, so I had to kill it. So here, now, this circuit doesn't matter anymore. So I'm going to just symbolically remove this, but that's what the point of the switch. Now, when I close this, the charge has nowhere to go on this circuit over here, so it's going to flow through my resistor. And let's see what happens. Close this, and you can see that the charge is flowing. The charge is flowing, and hopefully slowing down. Let me see if I can get a ammeter. Whoops. And my circuit is on fire. Help, someone. Sorry. Sorry if I'm the only one amused by this. Let's see. Let's get our current working here. Oh, great question from Francis in the audience. How is the current flowing if the battery is not involved in the current setup? Great question. I'll answer that in just a moment, Francis. What I want to do, anyway, it's just taking too long. So what's happening is we started this circuit up. I put way too much voltage on the battery, so everything's on fire, and everything's exploding, and it's going too fast for the CPU to even keep up with it. So my bulb is on ultra hot setting right now, but it's slowing down. You can see that it's starting to slow down. I charged up this capacitor, and what's happening now is the charges that are on this capacitor plate are flowing through the resistor. We're getting a equilibrium of plus and minus charges, and that's where the charges are coming from. Okay, I get a question. I get a comment from the audience. I'm dying here laughing. Oh well, sometimes things blow up even when they're virtual demos. So I hope, Francis, that answers your question. We build up. Let me try to build this a little bit better without so much bloody voltage on here. Let's try 500 instead. And then, so I have nothing going on over there. I connect this guy, I connect this guy, and there you go. I blew it up again. Close that off. And now just to clarify Francis's question, let's remove this. I have two charged plates. I connect this, and then bam, right? I get charge flowing from this plate to that plate. It's going through the resistor, and then it dies off as a function of time, right? With this exponential decay. So does the battery like pre-charge the capacitor? Exactly, Francis, that's exactly right. So if we go back, if we can get back onto my lecture notes. So in this circuit that I showed here, there's no battery over here. I just came along and I'm saying that I charged the capacitor to begin with. I'm showing that explicitly in this lab. Okay, so what do we have? The point that I was trying to make was, you saw that that bulb glowed really bright because the current was flowing through it, and then it kind of died down, died down, died down. That's this exponential decay that we're talking about. This exponential decay, this time constant for the current that's flowing through the resistor, this exponential decay. It's large at first, dies off with time. The time behavior of this circuit is going to be given by this time constant, RC. So if I know the resistance of that light bulb, and I know the capacitance of that capacitor, I can tell the time constant right away. So bear with me, give me 1 second here, and I'll try to explain this a little bit better. And then I really invite your questions on this, because this is one of those ones where either you get it, or it can be seem very mysterious, and I don't want it to be mysterious to you because my circuit blew up. So let's take a look. This is our governing equation for the current, right? It starts at some maximum value and then decays off with time. This time constant, tau, why do we call it the time constant? Because if I say at t equals tau, if that time constant is, say, 5 seconds, then when I am at 5 seconds from the moment that I close the switch, I get e to the -5 divided by 5, and that is e to the -1. If you punch in e to the -1 in your calculator, right, that is, e raised to the -1, you're going to get a number 0.3677, blah, 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 27 digits. It never ends, actually. But if I round it off, it's about 30.37, right? So what this is telling me, is that after one time constant, if I figure out that the time constant is 5 seconds, then after 5 seconds, that current, which started at some maximum value, is going to have decreased to about 37% of its initial value. Okay, that's the power. That's the reason we care about the time constant, is it kind of signifies what's happening in your circuit and the amount of time that it takes to happen. So this curve kind of falls off, and when it reaches 37%, it's done most of its falling off, right? It's fallen off. If 37%, 100 minus 37% is, you've gone 63% of the way down, right? So that's what that means. If we go one time constant, we've fallen to 37% of our original. Another way of looking at this is, if I look at this equation, I don't want to scroll around too fast for you guys, sorry about that. But if I look at this equation, this number here, if I go out to if I go out to time equals 100, or if I go out to 500 or 10,000, e to the negative large number gets small. It never quite actually hits 0, right? But I can figure out when it gets to a very small value. And how do I define small? It's arbitrary. But if I could say, hey, if this gets to the point where my current has fallen to less than 1% of its initial value, I could say, hey, this is almost done. It's pretty much all of the action has happened already, and that's what happens at 5 time constants. So again, RC if we have the resistance value and the capacitance value, I can get the tau value. And tau tells me the time constant. At one time constant, we've fallen to 37% of our original value. At 5 time constants, if I plug in the numbers here, 5 tau divided by tau gives me e to the negative 5. E to the negative 5, if I punch that into my calculator, is a number that is about 0.007. This signifies less than 1%. If you remember, 0.01 is 1%, then this has gotten to a value that's less than 1%. So 5 time constants gets me to the point where it's pretty much done. 1 time constant gets me to the point where a lot of the action has already happened. So in between 1 and 5 time constants is where most of the action, happens here. So again, this is, something like one time constant is going to get you down to 37%, and then 5 time constants is going to get you, within 1% of being done. Okay, I am a terrible drawer, so let me show you, I have a better picture here of this. And maybe if we focus on, let's take a look at the current in the bottom here. So we start at some maximum current. After 1 time constant, we've gotten to 37% of the original. After 5 time constants, it's basically down at 0 because you have less than 1% of the initial current still existing there. I'll loop back to this top plot in a moment. I need to introduce one more equation before we can talk about that. Okay, so again, I hope maybe you've seen exponential behavior somewhere in your studies before. It does pop up again and again in biology and nuclear physics and chemistry, in regular physics, and all kinds of stuff. And I hope you've seen it. Why does the capacitor voltage increase as time goes on? That plot is, pretend you didn't see that plot. I didn't introduce that equation yet, Francis. Thanks for the question. That was for the circuit that I'm about to show you, okay? So the next circuit that I'm about to show you is if we're charging a capacitor. Let me just give you one last numerical example, Francis, before I answer your question about, that increasing voltage. So in our simple circuit that we have here, a capacitor and a resistor, if I have a 10 ohm resistor and a 0.1 farad capacitor, I have a question from the audience. Can I please stop on page 10 for a second? I'll happily do that. Let me go back to page 10. Okay, give me a thumbs up or a okay when you got what you need from there, Catherine. Okay, so numerical example, just to take some of the mystery out of this. If I have this simple circuit, when I close that switch, the current's going to flow from the capacitor through the resistor. The behavior of that current and that voltage is going to depend on a time constant. If I have a 10 ohm resistor and a 0.1 farad capacitor, then my time constant is 1 second. After 5 seconds, that current is going to have flown and reached to less than 1% of its initial maximum. Okay, so there's our numerical example, just to take away some of the mystery of that. The second circuit that I want to introduce is slightly different. It's how would we charge this capacitor to begin with? So I want to introduce this circuit. I have a resistor, our old friend, the jagged tooth resistor, our old friend, the capacitor, which is just a parallel plate. I have this switch that's open. When it's open, nothing interesting is going to happen. And then I have a battery. And I mentioned to you a couple times that sometimes we use this weird epsilon to talk about the voltage or the potential difference across the battery. It's short for electromotive force. It's just a potential difference. There's nothing mysterious about it. But we want to use a different symbol here because we're going to have a potential difference across the capacitor. And I want to just, I want to have a delta V over here. And just to discriminate the variables, I use a different variable for the potential difference across the battery. Nothing new here, just a different symbol than we've usually used. But this is creating a potential difference, and that potential difference, eventually we will have a potential difference across this capacitor because of it. So current will flow when we close the switch, and that'll charge the capacitor, right? The current is the same thing will happen as we had before. In this case, when I close the switch, that positive current will flow through the resistor until it hits here. The capacitor has either vacuum or a dielectric in between here. A dielectric is an insulator. So you cannot flow current, you cannot flow normal current through this capacitor. It just hits kind of a brick wall. So what happens is I have a flow of charge. That charge will come over here, build up on this plate, and stop. We'll have positive charge on this plate. It will induce a negative charge on this plate, and then once they are kind of balanced, that flow of current drawn from the battery will stop. So again, we have this exponential decay of the current as we're charging that capacitor. At 5 time constants, it's 99% charged, right? So that's what we mean by 5 time constants. So this behavior, again, is the same exact equation, and the tau is exactly the same. If I know this R and I know this C, then I know the time constant. So the capacitor will charge until, this is the tricky part, and looping back, Francis, thank you for your patience on this. You asked me this maybe 10 minutes ago. Why does the voltage increase? Well, the capacitor will charge until the voltage matches the battery voltage. And the equation for this is this. It looks a little bit weird, but if I neglect what's in the parentheses here, this is the battery voltage, this is the capacitor voltage, and I have a 1 minus this thing here. This thing here gets smaller and smaller and smaller as time goes on, as that T gets bigger and bigger and bigger. So 1 minus something that gets smaller and smaller and smaller is something that gets bigger and bigger and bigger. And this is what that looks like. So thank you for your patience on that. I'm sorry I flashed this picture up a little bit early, a little bit prematurely. But that's what's happening here is I close that switch. The initial potential difference across this capacitor is 0. As this charge gushes out of the battery and slams up on the capacitor plate, that potential grows through this what's called the transient period. And then after about 5 time constants, all the action is done, and pretty much you're very close in potential difference across this capacitor by what is being provided by the battery. So Francis, okay, Francis says that makes sense. There we go. I'm super happy that that makes sense. So this is our second circuit. One thing I want to note, that if you take t to infinity, or just even very large number, punch in e to the negative 100 on your calculator, you're going to get a tiny number. And if you take that to infinity, this basically goes to 0. So this whole thing, we get 1 minus 0, which is just 1. At large T, delta VC is equal to this epsilon. In other words, the potential difference across the capacitor at large time is equal to that battery voltage, because we've closed this circuit and things just match up, and it doesn't matter anymore that, after that initial transient burst, things get to a steady state, and we'll have the same potential difference across this capacitor as we have across this battery. Okay, and that is, I think that's pretty much what I wanted to do. This is a poorly drawn version of this nice picture over here. Maybe it's a little bit more simpler, so I'll close this one. That delta V, as a function of time, we start at 0, we increase. Eventually it's going to match the potential difference across the battery. Okay, why am I introducing these RC circuits? Because these are good models of all kinds of things in life, from turn signal in your car to time-dependent flashing things, to nerve impulses in your body and processes in your cells. And I hope that we'll be able to kind of look at some of these neat applications of this. But the heart of it is we have a resistance and we have a capacitance, and we get a time dependence that is predictable and knowable and calculable. And so if you know the R, you know the C, you're going to know exactly how much that time constant is. There's one last numerical example that I have here, and that is if in this circuit we had 5 ohms as my resistance and my capacitance is 10 microfarads, well, forget about all the other math. I just multiply these two together to get the time constant. I get 5 times 10 is 50. This micro is a 10 to the minus 6 type creature. So we get 50 times 10 to the minus 6. An ohm times a farad is a second. And my time constant is going to be 50 times 10 to the minus 6 seconds, or more simply 50 microseconds. So how long is it going to take for this to get out of the transient phase, that burst of initial flow of current? About 5 time constants, and 5 time constants here is 5 times 50 microseconds, 250 microseconds. Okay, so that's what we got for today. Thank you so much, really for the feedback in the chat. That really helps direct where I should go with the lecture. I appreciate it and value it. Sorry I blew up the circuit and caught the lab on fire. Hopefully no one was hurt. Good luck on the weekend, and don't forget you have an exam coming up on Monday. I think we'll have much more information on Canvas about the structure of that. Do we have any more questions from the class? Nope. Okay. So I hope you have a great day, and I will see you all soon. Thank you for your patience, and thank you for your questions.